Hello and welcome to this short lecture on contact mechanics. It's a two-part lecture where we will discuss what kind of stresses that occur when two surfaces are put in contact with each other. My name is Roland Larsson. I'm a professor at Luleå University of Technology in Sweden. The lecture is planned according to this outline. We will discuss the contact of mainly non-conformal bodies. We will look into the elastically deformed surfaces, but also into plastically deformed surfaces. I can also recommend you to read Anton van Beek's book in chapter 4.1 if you want additional information. So first of all, I want you to think a little bit on this problem. What is the contact pressure if you put a steel ball in contact with a steel surface, or if you press your pen in contact with a paper, or you think about a tire on the road? What will the contact pressure be? You can discuss that with a friend, or you can just stop the movie clip here and think about it yourself. Well, I hope you have been thinking about it a little bit, and I hope we will learn during the course, during the lecture, what approximately what this contact pressure is. All right, let's continue. Another question you can think about is what is actually determining the contact pressure and also the deformation of the surfaces when you press two surfaces into contact. That's also, you stop the movie clip and discuss it with a friend, or discuss it by yourself. Think about it. Well, we will learn this also, I hope. Okay, think about this now. Here it's two surfaces. This is one surface, and up here there is another surface. So it's this represents a rough surface, and we press this rough surface into contact with a flat surface. And at the moment here, at a load of 1000 Newton per meter, the contact is only in one spot, more or less. But when I increase the load slightly, then this contact grows, but still there is only one peak or one asperity in contact with the other surface. If I continue to increase the pressure, you see the surfaces are deformed. The upper surface here is, you can clearly see that the upper surface is deformed. Actually the lower surface is also deformed, but you can't see that as much because there was already an asperity here. But if I keep on increasing the load, suddenly two asperities are in contact. And down here in this graph you can see the contact pressure. So in this case the contact pressure in the first asperity is a little bit more than 1 gigapascal, so it's pretty high pressure in this case. These surfaces are made of steel approximately, and in the other asperity contact the pressure is a little bit lower than 1 gigapascal. And you can keep on increasing the force or the load, and then you get more and more asperities into contact. So this is what is happening. So now you see it's a 100 higher load than in the very first picture, and even 500 times higher load. Then you see that a big portion of the surface is in contact with the other surface. And in this case even 1000 times bigger load than the very first contact. Then we have almost full contact between the surfaces. This is theoretically how it behaves, but one should of course remember that a surface isn't this, even if it has this peakiness or asperities, it's still, there are asperities on the asperities. So even if so the contact shouldn't be that big as it is right now, but we will discuss that also later. We will discuss the stresses and deformations in non-conformal contacts, and non-conformal contacts are those in between surfaces which are non-conformal. Maybe not a surprise, but non-conformal means that they do not fit to each other very well. They don't conform to each other very well, like the ball in contact with the inner raceway of a ball bearing. And such a contact is represented by very small contact area, pretty high contact stress, high contact pressure here in the contact region, and also very high stress then too. The deformations are mostly elastic, but if the pressure becomes too high or if the stresses become too high, then you also have plastic deformations. We normally try to represent all surfaces by ellipses or ellipsoids. So if you can approximate your surface by an ellipsoid, you can also use something named a Hertz theory, which was invented by Hertz in the 1880s sometime, and use that theory to compute the contact pressure and also the size of the contact spot. A very brief introduction to Hertz theory is given like this. First of all, before you do that, we need to define a number of parameters. In Hertz theory, he didn't use two ellipsoids in contact with each other. Instead, he used one ellipsoid in contact with a flat surface. And what you do then is to try to find a kind of equivalent radii in the x direction and in the y direction, which is defined like this. So 1 over rx, the equivalent radius in x direction, is the same as the sum of 1 over rx of solid A plus 1 over rx of solid B, and the same is for y. There are also some sign designations important to remember. It's a difference to press a sphere in contact with another sphere in the outer surface of the other sphere, or if you press it into a spherical surface inside the spherical surface or inside the cylindrical surface. So actually you have to change the sign according to this, and it's a little bit tricky to explain, and we will maybe come back to that later. Some of the definitions is that you may have two surfaces made of two different materials. Two different materials with different elastic modulus and Poisson ratio. And in Hertz theory, you just compute a kind of effective elastic modulus. And you may also need a combined radius, which is the sum of the 1 over rx plus 1 over ry, and inverted. So it's a kind of combined radius of the two directions. What you also need is the load. So in a 2D case, you need the load itself, or if you have a cylinder on cylinder case, you need a load per unit length. So you will see that too later. In the Hertz theory then, or this kind of simplified version of the Hertz theory, you can compute the size of the contact spot. This is the contact spot, and it's since in the general case it's two ellipsoids in contact with each other, you have the size dy in the y direction and the size dx in the x direction. And these diameters can be found by from this expression. You see, load, combined radius, effective elastic modulus, pi, but there are two unknown parameters. We are coming back to them later. It's the epsilon and the k. These are functions of Rx and Ry only, so pretty easy to find approximate values of them. If you have a line contact, that's typically a cylinder in contact with a plane, you can compute the dx, the width of the contact, by using this expression. In that case, dy is infinite. From this approximate Hamrock and Brew, they've made some approximations of the epsilon and k function, and the epsilon can be found from this table, where the alpha r here is only the ratio between the ry and rx, and the k is the alpha r with the power 2 over pi. Actually, k is also the ratio of dy and dx, but since you don't really know dy and dx yet, you can't use that definition at the moment. So, if you compute dx and dy according to that, then you can find also the maximum pressure or the pressure distribution inside the contact. It looks like this. So it varies over the as according to this expression. It is 0 along the edges of the contact that you may expect it, and it has its maximum in the very center of the contact. And at this center of the contact, the pressure is pH, the Hertz pressure, what we usually call that, the Hertz pressure. And this Hertz pressure can be computed from this expression. For the line contact, it's the same, but there is no variation in the y direction because it's infinite length of that. And the maximum pressure is found from this expression. A special case is of course a ball on a plane. In that case, the Rx and the Ry are the same, and you can simplify the expressions a little bit, and you don't need the epsilon and the k's, and then the expressions look like this. You can also find an expression for the deformation of at the center. Please note also that some of you may read Anton van Beek's book, is that he's using a little bit different definition for the radii. So, but still the result will be the same, but just to mention it. Okay, let's use this very simple theory to an example, a ball on a plane. You can think about this. You can compute it by using this theory. You can compute the contact size. What is it? You can compute the contact pressure. What is it? If you know that the ball and also the plane is made of steel, it's the load is 100 newtons and the radius of the ball is 35 millimeters. Make a guess first, and then you use the theory and to check if you made a good guess or not. And that ends part 1, and we will see the solution in part 2.